Hello everyone, so in this presentation, I will walk through my responsible AI housing price prediction system. The goal of this project is not only to build an accurate regression model, but also to ensure the system follows the responsible AI principles, including the transparency, fairness, reliability, and accountability. This project focused on three main objectives. First one could be developing a robust regression model for predicting house prices, applying the explanatory AI technique to understand how predictions are made, and also evaluating the system using the fairness analysis, bias detection, and production readiness check. Throughout this presentation, I will reference specific sections from my notebook to explain each step of my workflow. So let's take a look in the first step. Analyze the target variable sales price. So in the target variable analysis section, the raw scale price distribution shows a strong right skewness with a skewness value of approximately 1.94. Such skewness can negatively affect the regression model because large outliers dominated the loss function. To address this issue, I applied a log transformation using log1p, which reduced the skewness to 0.16. After the transformation, the distribution becomes much closer to normal distribution. This improves model stability and leads to a more reliable error metrics. Therefore, all models in this project were trained using the log transform sales price. Next, I analyze some missing values. The missing value raised by feature visualization shows that most variables contain very little missing data. However, some features such as the pool QC, missed features, LA, and fence has extremely high missing rates. These variables represent the rare housing characteristic. In many cases, missing value actually means that the feature does not exist. Instead of removing them completely, I handle them using the domain-aware encoding, preserving the useful information. Handling missing values carefully is important for model readability, reliability, and responsible data use. So let's take a closer look on the explanatory feature analysis. So the notebook section in the top 15 numeric features correlated with the sales price. To understand better on the drivers of the housing prices, I perform correlation analysis. The top 15 numeric features correlated plot shows that the strongest predictors are including by overall quality, GR living areas, garage cars, garage areas, top BSMT, SF. For example, overall qual has a correlation about 0.79, indicating the construction quality strongly affect the property values. This relationship is also visible in the sales price by overall quality plot, where higher quality ratings corresponding to significantly higher prices. Similarly, the GR living area and sales price scatter plot shows a clear positive relationship between the living area and the housing price. These findings provide intuition for the feature's importance result later observed in the explanatory analysis. After pre-processing, I trained several models and evaluate them using the five-fold cross-validation. The model tested were ridge regression, elastic net, XGBoost. The result shows that elastic net achieved the best performance with a RMC around 0.11019, and cross-validation ensures that the evaluation is robust and not dependent on a single train test split, which improved the reliability of the model evaluation process. And to assess the model quality, I also analyzed the residuals. So the residuals versus the fitted plot shows that those residuals are centered around 0 and captures, which suggesting that there's no strong patterns and also suggesting the model captures the main relationships in the data. And the residual distributions is approximately symmetric. In addition, the actual predicted plot shows that the predictions closely follow the ideal prediction line. Together, these diagnoses indicates that the model is well fitted and does not shows a severe underfitting or overfitting. And in the next part, we're going to talk about some learning curve analysis. To further evaluate the model generalization, I generate some learning curve information. As the training size increase and training error gradually increase while the validation error decrease and stabilized. The relatively small gap between the two curves indicates a balanced bias variance trade-off, suggesting the model generalized very well and to unseen data. To improve the transparency on the local explanatory aspect, I use the SHAP values to interpret the models. So the SHAP summary plot is actually and also the global feature importance And main SHAP is also to see some problem in this aspect. To improve the transparency, I use SHAP values to interpret such kind of information, which shows both importance and directions to each feature impact. You can see here the most influential features include the total qual SF, total BAT, year since remote, and MSMT, UNAP SF, kitchen quality. These variables consistently contribute to housing price predictions. The global SHAP importance chart further confirmed the rankings by measuring the average contribution magnitude. These global explanations help the user understand which factors most strongly influence the predictions. And I also generate a partial dependency plot to visualize the feature effects. For example, increase the total qual SF steadily increase the prices. Similarly, large total SF and better overall conditions generally lead to a higher predicted values. These plots help the stakeholders understand how the model responds to the change in the key features. While global exponentials describe the overall behavioral, individual prediction requires the local exponentials. The SHAP waterfall plot breaks down a prediction into the contributions from the individual features. For example, features like total qual SF and the total BAS can push the predicted price higher, while the other features may reduce it. And SHAP force plot visually shows how this contribution combines to produce the final predictions. In addition, I implemented the Lime exponentials, which approximate the model locally using a simpler interpretable models. And to increase the confidence in exponentials, I compared SHAP and Lime result for the same instance. Although the two methods were using the different approaches, they identified similar influential features. Using the multiple exponentials method improved the interpretability and transparency. And also, I performed what-if analysis to simulate the prediction change when features are modified. So in this example, I vary the overall qual while keeping the other features constant. The resulting plot shows that how predicted house price respond to the quality changes, allowing the user to understand the model's decision logic. And let's talk about some fairness and bias analysis. The responsible AI requires the model perform fairly across the different groups. Evaluate the fairness is very important. So I evaluate fairness across the neighborhood groups and different price tiers. So for the neighborhood performance analysis, it shows that the prediction residuals and RMSE for each neighborhood. Importantly, none of these neighborhoods exceed up to 10% bias threshold. Similarly, for the price tier analysis, I compare the performance across the low, mid, high price ranges. Although some variation exists, but the difference remains quite relatively small. And to quantify the fairness, so several metrics were calculated. For example, the demographic parity proxy, equalized RMC ratio, calibration correlations, and overall MAPE. So the equalized RMC ratio is below 1.5, which indicating the relatively consistent performance across the price tiers. This suggests that the model achieved a reasonable level of fairness. And responsible AI system also monitor the data drift. So let's see some information on that. So the data drift detection report compares the distribution of the new data with the reference training data. All monitor features show a minimum drift, suggesting that the model should remain stable when applied to similar feature data. And also, finally, evaluate whether the model is ready for deployment. So this checklist shows 14 out of the 18 production criteria are satisfied, including the cross-validation training, model serialization, SHAP and Lime explanations, counterfactual analysis, fairness evaluation, data drift monitoring. Some items such as CI/CD integrations and monitoring dashboard are beyond the scope of this hackathon, but will be implemented in a real production environment. So in conclusion, these projects demonstrate how the machine learning system can be developed using the responsible AI principles. The system combines a strong predictive performance with transparent analysis, explanations using the SHAP and Lime, fairness evaluation across the neighborhoods and price tiers, bias detection and ethical analysis, production readiness considerations. By integrating the predictive modeling with the interpretability and fairness evaluations, this approach supports ethical, trustworthy AI deployment in a real-world decision-making system. Thank you.